Hello everyone, and thank you for joining us in today's webinar entitled Optimizing Electric Motors Performance Using Asymmetric Design Method. My name is Farnam and I am an electric motor design engineer, and in today's webinar we're going to talk about different aspects of the asymmetric design methodology, its application in PM machine design, and we're going to also conduct a comparison study in order to show how asymmetric design can help us to improve the performance of the machine by using EMWorks 2D software. The EMWorks is a leading company in providing solutions for performance analysis of electronic and electrical devices for a wide range of applications. And in today's webinar, the agenda will be like this. First, we're going to talk about the market of electrical motors and its requirements. We're going to talk about why the optimization of electrical motors is very important due to current needs. And also, we're going to talk about how asymmetric design can help us to optimize the machine performance. The definition of the asymmetric design method will be the first step of our presentation. To dive into the details of the asymmetric design method, we're going to talk about what is asymmetric design method, and then we're going to talk about why asymmetric design can be considered as a choice for improving the performance of the machine. More specifically, the permanent magnet machines that also consists of reluctance, torque. We are going to talk about the machines such as interior permanent magnet machines that both have both of magnet torques and also the reluctance torque. And then we're going to talk about the design choices that we have to make when we want to adopt and use the asymmetric design method, when we want to implement it in some specific application. Then, in order to see how it works, how this method works, can help us, we're gonna talk about the comparison study specifications. We're gonna use the data collected from EMWorks 2D to demonstrate the performance. When we conduct the performance analysis, we're gonna talk about different aspects such as torque and current angle curves, the ripple rate and Cogging torque, and then we finish our presentation with conclusion. Well, without further ado, let's talk about the market of electric motors. As we all know, electric motors cover a wide range of applications, and it is an inseparable part of today's industry, from medical devices to home appliances, transportation systems, or even advanced technologies and applications such as space exploration. As you can see here, we have a data that's showing that global electrical car sales has been doubled in 2021. Showing how important it is to focus on electric motor design optimization, because as we go further in the industry, we need better performances, better efficiencies, and therefore it is very important to use proper solutions, proper design techniques in order to achieve better performances. As we can see here in this diagram, it has been shown that the main aspects of the design optimization of electrical machines consists of two main parts. First is the initial design, that where we should choose the motor type, its topology, and also the material we're gonna use in order to build our prototype and also the final product. Also, we have to consider the electromagnetic performance, structural performance, and thermal performances. Also, we have to also consider the control aspects of the machine from perspective of power electronics and inverter and controller part. And at the end, we can consider the design process, the manufacturing process, the difficulties and possible flaws during the prototyping process. But here, on the other hand, we have the optimization part, where we can adopt the intelligent algorithms such as genetic algorithm, particle swarm algorithm, or even we can consider different modeling techniques such as surrogate model based optimization methods, multi-level optimization, multi-physics optimization, etc. As a conclusion of this part, as you can see, before doing anything further, before initiating the whole optimization process, we should first choose a proper motor type and topology. And here, it is the most important part, that the asymmetric design method shows its power, and it shows the basic of the machine design is gonna be on the geometrical changes that we adopt in the first stage. So here, as you can see here, first we're gonna talk about the definition of the asymmetric design method. The asymmetric design method is, we can define it as changing and applying asymmetricity to the geometry of the machine in both, for instance, cross-sectional and also axial directions. For an example, as you can see in the right hand, the picture is showing us a conventional permanent magnet machines, interior permanent magnet machines with an example permanent magnet configurations. And here you can see a symmetry line and a mirror part completely identical to the right side of the rotor part. But on the left hand of the picture, we are seeing a picture of a machine type that is asymmetric, and we have applied asymmetricity to the machine topology by means of using a flux barrier in addition to the whole structure. As you can see, by adding this flux barrier, we created asymmetricity, and as we can expect, we will see a different performance, different torque compared to initial and conventional symmetric design. This is the base definition of asymmetric design method from perspective of geometry. But from perspective of permanent magnet machines, in the literature there has been a categorization focusing on different configurations of permanent magnet and also the rotor core structure, and how we can adopt the asymmetric design method. As you can see here in the group 1, we have a combination of permanent magnet and rotor core, where both have symmetrical configuration and structure, but there is a displacement angle, and the motor from the rotor part is asymmetric in axial direction. As you can see, the first part of the machine is like a SPM motor, surface permanent magnet motor part, and also the end of the rotor is a reluctance rotor. And as you can see, there is a asymmetricity in the axial direction. In group 2, we have a completely symmetrical configuration of permanent magnets, but in cross-sectional perspective, from perspective of cross-sectional view, we have an asymmetric rotor structure, and as a result we can also call it asymmetric design. In group 3 also we have an asymmetric PM configuration, and the rotor is symmetrical. And in group 4, both PMs and rotor cores has asymmetric configuration, and also it can provide a different performance compared to other 3 groups. As you can see, we are dealing with different approaches. There are different options to adopt asymmetricity during the design, giving us different options. When we want to, for instance, target a specific performance, we can adopt one of these groups, or even come up with new ideas during the design. And now let's talk about why asymmetric design can be a helpful approach to improve the performance of the machine. But first we have to note that electric motors performance improvement is a multi-physics problem. So we have to, when we want to improve the performance, we have to consider alongside the electromagnetic performance, we have to consider the thermal and also the mechanical aspects, or even the control part of the machine. But here, when we want to adopt the asymmetric design approach, we're going to focus on electromagnetic performance of the e-motors, and more specifically the torque characteristics that we are going to focus on, because this torque characteristics have been always a matter of interest for e-motor designers. When they want to reduce the volume of the machine, they want to increase the torque density, and as a result power density. Also they want to minimize the ripple rate. But in general, before analyzing the motor and when we want to design a machine, there is a very popular and famous formula that helps the design engineer to initiate the design process. And as you can see here, electromagnetic torque is a direct function of winding factor, magnetic loading, electrical loading, and the dimensions of the machine. They are directly proportional and directly related to each other. And as you can see here, for instance, by changing a magnetic loading parameter, we can increase or reduce the electromagnetic torque. And since we desire to reach higher torque values based on the constant dimensions, we can play and change these variables, these parameters, by changing the geometrical parameters of the machine, leading us to a better or worse electromagnetic torque. And here we can see a symmetric interior permanent magnet machine topology that follows the same rule. Also, we can describe the torque characteristics of the machine, especially the synchronous machines. Here, for instance, we have the AIPM motor's torque as a function of current amplitude and phase, current phase. Here we have the equation. Let me my laser pointer to help you have a better understanding. Here, this is the very famous formula describing the performance of the machine as a function of current amplitude and also the current angle or phase angle. The AIPM motor torque consists of two parts. First, the magnet torque, which is pure magnetic torque as a result of the magnet flux linkage and interaction between the stator field. And also we have the reluctance torque, which is a function of the saliency ratio or DQ and DQ axis inductances and its difference actually. And by changing each of these variables, we can change the value of the torque. And here we have also defined the current angle here to show what we are meaning, but what the alpha is meaning here. And as you can see here, the curves also is showing us the difference between the peak of the magnet torque. Here is being represented by the blue color, and also the red color is showing us the reluctance torque. And the combination of these two torques gonna give us the real torque of the machine. And here we have the maximum torque operating for, or as an abbreviation of MTPA, that we are each time we are trying to focus to analyze the performance of a machine in this area. But here we want to show that what happens when we adopt asymmetric design method. The first effect undoubtedly gonna be on the average torque that we showed in previous slides. As you can see in this formula, we have it is similar to the base formula of the synchronous machine, but here we added a new variable called a phase shift due to asymmetricity. This what happens here first, as you can see here, we can change the saliency ratio by applying asymmetricity to the topology, to the geometry, and we can change inductances, right? And we can play with the value with the amplitude of the reluctance torque. But also we can change the position of the magnet and reluctance peak torques, where we can close the gap between peak of the magnetic torque and also the reluctance torque. And as a result, by combining these two curves, we can reach higher final torque. And this is one of the unique results of asymmetric design. We can create this phase shift, and it can help us to improve the torque. But also we can change the PM flux linkage, because for instance in interior permanent magnet machines, by changing the barrier width or barrier length, the place that we put the magnets, we can also change the dimension of the magnets, and as a result we can change the PM flux directly affecting the magnetic parts. So as you can see here, the asymmetricity can influence each part of this formula, and as a result it can change it to better or worse by taking a step completely wisely and calculating the performance in each step. We can make sure that our targeted performance will be improved by using asymmetric design. But the benefits of the asymmetric design is not limited to the average torque, but there have been a very significant achievements in terms of reducing the ripple rate and the cogging torque of the permanent magnet machines. The literature shows us there has been lots of research and provided data showing us the cogging torque, for instance, in this topology. By adopting this topology has been reduced significantly from this waveform, which is a conventional PM machine, to this waveform, and as you can see, the peak value has been significantly reduced by adopting asymmetric design. And also on the left hand side we have a machine which is axially asymmetric. It has an axially asymmetric topology, and the torque rate in the maximum torque operation point of the machine has been significantly improved compared to conventional permanent magnet synchronous machine, or as an abbreviation PM CNRMs. And all of this data is showing us that adopting this method can also be an helpful tool to achieve better performances and a smoother operation during the machine's operation, and also we can get a better performance compared to conventional design without using methods such as SQing methods or different design methods. Anyway, now after we talked about the details of the asymmetric design and how it can be considered as a helpful tool, we have to come up with proper asymmetric design approach. For instance, we have to make a choice between available categories. For instance, we want to use axially asymmetric design method, or other groups we can apply a symmetric configuration of the PMs, but simultaneously we can use asymmetric rotor core, etc. So first step gonna be choosing a proper asymmetric design approach and category, and after that we have to initialize the design procedure by coming up with initial design by using the design formulas, and also we have to considering a comparison with symmetric one, because it is very important. The design formulas are basically will give us general performance characteristics, but not a detailed ones. So it is good to have an understanding on both design, and always bear in mind that comparison can be a good approach when we want to make sure that our performance is improving. And in order to analyze the performance, we have to simulate before doing any prototyping or even manufacturing, because it can be costly. So we have to use computer-based analysis. And in terms of permanent magnet machines, there are various aspects that we can consider, but here the main objective here to improve the torque current angle curves. We want to achieve higher torque when we are analyzing the torque current angle curves, and also we want to have a smooth operation. We want to minimize the torque per rate at different operation points, especially the maximum torque per ampere operation point in different, for instance, with respect of different current amplitudes. And also we want to minimize or reduce the peak Cogging torque value, because it works like a brake when we want to start the motor, and it can influence the operation of the machine in a bad manner. It can make it worse. So we want to make sure that also the Cogging torque is tolerable and acts in an acceptable range. So in order to do such a study, the ENWorks 2D is a great software tool, but the ENWorks itself providing wide range of solutions, from template-based motor design to 3D finite element analysis environment. The study we have done has been based on the ENWorks, and the results were reliable, and it helped us to have a better understanding of the asymmetric design method, its drawbacks, its pros and cons also. And the result that we obtained was very interesting. First of all, the specifications that we were looking for, we managed to get it from research papers. Here, as you can see in the right hand side, here is a picture of an asymmetric machine from literature that we mentioned in the references part. Here the IPM that this reference has proposed is asymmetric from perspective of the length of the magnets and the barrier shape. As you can see here, for instance, we can change the position of the middle breech. We can work with this barrier like a fluid. It can change the middle point, and as a result it can change the D axis and the direction of the magnetic field, and also we can change the shape of the magnet. We can create an asymmetric design. And as you can see here, this machine that we have designed and for comparison study, it contains a permanent magnet 4-pole machine that the length of the magnets in the barriers are different from one another. So as a result, you can see that we adopted the group 4 from categorization of the asymmetric design, where the permanent magnet configuration and also the rotor core both are asymmetric. And here also we have a initial symmetric IPM machine, which is conventional, and these are the basic specifications that we work with. The stator is completely identical with 36 slots. The speed of the rotation was 1,500 RPMs. The winding was single layer and distributed. The current amplitude was 38.7 amperes. All of the design dimensions were fixed, the material, and then we only changed the rotor part in order to conduct a comparison study based on the ENWorks 2D software. And here we have a picture showing the general steps of the ENWorks 2D when we want to conduct a performance study. We can use the material library. It covers wide range of the suppliers and the data for material, which is very important in case that we want to conduct a finite element analysis. Then we have to also define the boundary condition, vector potential, and also when we want to calculate the forces, we also have to make sure the properties are okay, the configurations are well. We have also the mesh control. We also have to make sure that excitation part is correct. Therefore, we also have to introduce the windings. And after we finalized the performance study requirements, we conducted the performance analysis. The first target that we were talking about, it is very important to analyze, is to, as I mentioned earlier, is the torque current angle curves. And as you can see here, we have 6 curves. 3 of them is representing the characteristics of the IPM machine. The blue one here, where the peak is 13.88, is the total torque at the MTPA operation of the conventional IPM machine. And here also, the yellow one also is representing the asymmetric IPM machine total torque. And as you can see, by adopting the topology, by this design approach, we have increased the torque value from 13.88 Newton meter to 14.16 Newton meter, which is a increase of the torque. What happened here? We increased the reluctance torque, as I mentioned earlier in the formula, that we can play with each of these variables in order to reach higher torque values. And here we increase the reluctance torque at the beginning, and also the magnet torque has been reduced because we use less magnet volume, and it's showing us that we achieved a better performance of the torque with lower magnet volume, material. And as a result, the ending was desirable, and we achieved a higher torque. And from perspective of the shifting phase, the shifting angle also, as you can see here, there has been a little change. In the literature also has been shown that the focus was on torque improvement instead of only the torque production, which we have shown and analyzed in the next step, where we achieve a significant improvement in the torque ripple rate. As you can see here, the blue color is showing an IPM machine, conventional symmetric machine, and the red one is showing the asymmetric IPM machine torque waveform in the 60 electrical degree, because the torque of the three-phase synchronous machines has a period of 60 electric degree, but here we also consider the 1 electric period or equal to 360 electrical degree. And as you can see here, the ripple has been reduced from 73.93% to 90.19%. I have to mention that we didn't use any torque ripple rate compensation method, such as skiing or other techniques, such as adopting notch on the surface of the machine. This rotor, as you saw, has a very simple structure, and the method that we use help us to significantly reduce the ripple rate of the performance of the machine in the maximum torque per ampere operation point. It is worthy to say that the factors influencing the performance of the machine and ripple rate is usually are based on air gap flux harmonics, the Cogging torque itself, also the time harmonics of the stator current, and the saturation of the rotor or stator cores. But here the main focus has been on the air gap flux harmonics and the Cogging torque, because when we change the position of the magnet, and when we apply the asymmetricity, we change the air gap flux distribution and also the Cogging torque. And here in this slide we have analyzed also the Cogging torque of the machine. As you can see here, the red one is the Cogging torque waveform of the asymmetric IPM machine in 10 mechanical degree, because as you can see, the Cogging torque period is a function of number of slots and poles, and here, since we have 36 slot, each slot pitch gonna be 10 mechanical degree, and here we have that period. As you can see, the blue one, which is the conventional IPM machine that we use in the first stage, has a peak torque of peak value of 1.14 Newton meter. But by adopting the asymmetric design approach, we have reduced it to very low value of 0.056 Newton meter, which it's like we have guaranteed very smooth operation compared to initial design, and this is all because of adopting the asymmetric design approach. And the results proves that the previous research, the data collected from previous research is also correct, and the asymmetric design can affect the torque characteristics in a way that we can expect better performances, especially lower torque ripple compared to conventional symmetric machine designs. Well, as a conclusion of this webinar, first we talked about the concept of asymmetric design of the e-motors, and we talked about how we can apply it, how we can adopt it when we want to target the torque improvement part of the design. And in order to demonstrate the theoretical background, we conducted an example case study by using IPM motors with symmetric and also asymmetric configurations, and at the end the results showed us a higher average torque can be achieved while the magnet volume can be reduced, which is very important in terms of, for instance, creating a function like torque per dollar or torque per volume. These are very important output functions, cost functions. Actually, electric motor designers must consider. But the most significant achievement was related to the torque ripple rate. The torque ripple and cogging torque has been significantly reduced when we adopted the asymmetric design, showing us the asymmetric design approach can be a useful tool and approach in terms of providing better performance, a smoother performance compared to conventional design, without adopting any other approaches such as skewing or notching the surface of the rotor core. And here is the references that we used in order to conduct the comparison study, and also the technical details related to recent research. Thank you for again, thank you for joining us, and now if you have any question, I'll be glad to answer them. Thank you.